Hello everyone, my name is Anudh Mishra. I am an MBBS student at AIIMS Bhuvneshwar. Today I'm going to cover the topic hydrocarbons with you, and this is basically the first chapter of your organic chemistry. We consider this as a very basic chapter which you need to learn, which you need to study before you can begin your journey in OC. Okay, this chapter basically deals with different types of hydrocarbons. We'll deal with the definition first. We'll define how what a hydrocarbon is. Excuse me. Then we'll move on to different types of hydrocarbon, their properties, physical, chemical, examples, special points about them. And at the end of the session, I will solve some previous year questions of JEE-Main. The whole session is going to be in the point of view of JEE-Main, keeping that your JEE-Mains are scheduled in Jan. So keeping that in mind, we'll try to cover as much as possible. Let's start. What is a hydrocarbon? Classically, it is self-explanatory, means compounds of only carbon and hydrogen. No oxygen, no nitrogen, no other element. Only carbon and hydrogen. Examples are LPG, CNG, right? Moving on, classification. So, depending upon the types of carbon-carbon bonds, they are saturated, unsaturated, and aromatic. So these are the three types of hydrocarbons: saturated hydrocarbons, unsaturated hydrocarbons, and aromatic hydrocarbons. So saturated hydrocarbons, only single bond is there. Only single bonds are present. Unsaturated, at least one or more than one double or triple bonds between carbon are present. And aromatic is a special condition which we will deal with later. You have to remember that the saturated hydrocarbons are represented by alkanes and unsaturated are represented by alkenes and alkynes. Aromatic hydrocarbons have a lot of examples. The classic example which we give is benzene. So let us move on to the saturated hydrocarbons, alkanes. They only contain carbon-carbon single bonds. No double bond is there. The first member of alkane is methane. I hope you all know what a homologous series is. Okay. Homologous series is like they have a general formula. They have a general formula and they have members which have this, which fall in this general formula. The chemical formula falls under this general formula only. Yeah. They have given the general formula for alkanes to be CnH2n plus 2, where n, the lowest acceptable value of n is 1. Okay. So if you put n is equal to 1, you'll get methane, CH4. Putting n is equal to 2 will give you ethane, C2H6. And each homologous series will differ by a CH2 group. Okay. The difference between each homologous member of a homologous series will be 1 CH2 group. You add one CH2 group, it will become the next member. Then talking about methane, it is an sp, according to VSEPR, it has a sp3 hybridization. The 4 hydrogen atoms lie on the 4 corners of a regular tetrahedron. Bond angles are 109.5 degree. Classic example of sp3 hybrid orbitals in the carbon. Okay. Then nomenclature and isomerism. How do you name an alkane, and what is isomerism in alkane? So naming an alkane is really simple. You need to know the basic terminologies like If there are one carbon, there are two carbons, what to call it, right? Meth, eth, prop, but, and just add the suffix ane. Okay, for alkanes, you have to add the suffix ane in the end. Count the number of carbons and add the suffix ane. For example, if n is equal to 4, it is butane. Okay. Then what isomerism is? Isomerism is defined as the compounds which are having same chemical formula but having different structures. That is, they are isomers. Examples of isomers: this is butane, this is 2-methyl propane or isobutane. These two are having the same formula, that is C4H10, but you can see the structures are very, very different. Butane, it is arranged in a straight chain, but in 2-methyl propane or isobutane, it is branched. So this is an example of structural isomerism. Okay, these are structural isomer, and if you even classify them in what kind of structural isomer, they are chain isomers because the chain length is different. How? Look at the chain length here. It consists of your 4 carbons, but the chain length here is only consisting of 3 carbons. So chain length is different. Other examples of chain isomerism are pentane, 2-methyl butane or isopentane, and 2,2-dimethyl propane or neopentane. They are also structural isomerism and more specifically chain isomers. Now, based on the number of number of hydrogen, based on the number of carbon atoms attached to the carbon atom, they are termed as primary, secondary, tertiary, or quaternary. Just I will give you structural examples to clear this. This is a This is a compound. This is a hydrocarbon. Just a second. This is a given hydrocarbon, and this is the exact structure of that hydrocarbon. Now, look at this carbon. This carbon is connected to only one other carbon. So, this is primary. Look at this carbon. This carbon is connected to 2 carbons. So, it is a secondary carbon. Look at this carbon. This is connected to 3 different carbons. So, this is a tertiary carbon. Finally, look at this carbon. This is connected to 4 different carbon atoms. So, it is a quaternary carbon. Now, the hydrogen which are attached to these carbon atoms, suppose to this carbon atoms, 3 hydrogen will be attached. To this carbon atom, only 2 will be attached. To this, 2 will be attached. These hydrogens are also named according to the carbon. This is a primary hydrogen. This is a secondary hydrogen. Quaternary page, there is no possibility of adding a hydrogen. So on tertiary, this is a tertiary hydrogen. Moving on, let us recall the general rules of nomenclature. See, these are some examples of how do you name compounds. You have to cover this on your own. They have given some remarks, some points which define how and why these compounds are named as such. Go through these. I will suggest you do not skip anything in NCERT for JEE-Main. Okay, JEE-Mains nowadays it is completely NCERT based. If you skip NCERT, you might miss some relevant points. Of course, you might be covering other materials which are more competitive, but NCERT has to be finished first. They give direct questions from NCERT, which many of the aspirants are not able to solve. They lose marks, which is not acceptable, right? When you have a textbook in your hand and I'm guaranteeing you that most of the questions will be based on this textbook, then why don't you complete it? Why do you want to lose marks just because you didn't read your standard textbook? Always complete NCERT before attempting the paper. Maximize your chances of getting a good rank. And yeah, question practice on top of that will increase those chances further. Now, see, how do you write the structure from the name? So the name is 3-ethyl 2-dimethyl pentane. Now, because it is pentane, you draw a 5-carbon chain. You number it. Okay, next. You according to the number, you place the substituent. Okay, then satisfy the balance of the main carbons by attaching hydrogens. You have the correct structure of 2,2-dimethyl 3-ethyl 2,2-dimethyl pentane. Okay, then comes the main part which you have to mug up. Yeah, you have to mug up this preparation of alkanes from unsaturated hydrocarbon. Process is known as hydrogenation. Catalysts are platinum, palladium, nickel. So yeah, all the double bonds will be consumed. Even if it is an alkyne or it is an alkane, all the double bonds will be converted to single bonds. Next is from alkyl halides, except fluorides. What is the catalyst? Zinc and dilute HCl. So yeah, you remove the halide and you add hydrogen there. Okay, got it? Simple. Remove the halide, add hydrogen. Remove the halide, add hydrogen. Okay. Alkyl halides on treatment with sodium metal. This is the second reaction on which you can add how to convert alkyl halides to alkanes. The reaction is known as Bode's reaction. Catalyst is sodium metal and dry ethereal. Okay, give higher alkanes. Okay, what is higher alkane? So what is happening basically is you're removing halide from both and joining the hydrocarbon part of two. Okay, see, so it will never give you CH4 because it has only one carbon. Now C2H5, join them. Remove the remove the halide and join the hydrocarbons. This is how you do a Woods reaction. Now, how to prepare them from carboxylic acids? So, what are the substrates? Substrates are sodium salts of carboxylic acids. What is the catalyst? Soda lime. Okay, mixture of sodium hydroxide and calcium. And you heat it, they give alkane. So, what happens is you have to, if this is the this thing acidic salt, then you just remove COONA. Okay, remove CONA and add a H. So you get the okay. So general formula is RCOO minus Na plus. If you treat it with soda lime, you will get RH. They have given the mechanism. You ought to study the mechanism on your own. Properties, physical properties. What can you say? They are non-polar. Okay, they possess weak van der Waals forces. So they 1 to 4 are gases, 5 to 17 are liquids, more than 18 are solids. What is the boiling? Okay, they dissolve in like dissolves like concept. So these non-polar substances dissolve in non-polar solvents. The boiling point increases steadily. There is a steady increase in boiling point with increase in molecular mass. Okay. Now, chemical properties, substitution reactions will be shown. First example is halogenation. In substitution reaction, what happens? A halogen hydrogen. These reactions are reverse of the preparations. So yeah, you get a alkyl halide. One more hydrogen is removed. So you get this. One more hydrogen is removed. Again, one more hydrogen is removed. This. Okay. Next. See, one more hydrogen is removed, and you get. Just do that. They have given the mechanism. It proceeds by free radical mechanism, substitution reactions, free radical mechanisms are shown. This is initiation step. You create a free radical. Propagation step. That free radical attacks a normal molecule, generates more types of free radicals. These more types of free radicals again attack and generate the previous free radical. See, they have generated the parent free radical. And these steps continue. Termination step is two free radicals combine together and they terminate the reaction. So initiate, maintain or propagate, and then terminate. This is how you do a chemical reaction. All right. Moving on. Combustion. Just burn it in presence of oxygen. General combustion reaction, you can just look at it. Don't need to remember. You can always derive it. Controlled oxidation, remember these three examples as they are written. Okay, with the catalysts. Done. Four examples actually. Then you have isomerization. What is an isomerization reaction? It is converting an straight chain alkane into a branch chain alkane. So straight chain alkane to a branch chain alkane, and alkanes to branch chain alkane. This is isomerization. What is the catalyst? Anhydrous AlCl3 or HCl. Aromatization. Aromatization. Alkanes having this. How do you convert them to benzene? So yeah, the catalysts are given. If they are more than 6 carbons, you can make a benzene out of it. Just you need. I'm just brushing up. You need to study this beforehand. Reaction with steam. Nickel is the catalyst. You get this characteristic water gas reaction. Pyrolysis is breaking up an alkane into small alkanes in presence of heat. Then the catalysts are platinum, palladium, and nickel. Conformations. Conformations are like a molecule has infinite conformations. You can rotate it along a single bond any number of times, any degrees you can create. So yeah, conformations are just rotations along a single bond. First kind of conformation, see, Sawhorse projections are projected like this. Newman projections, you must have seen. These are two conformations, represented in Newman's projection, corresponding to ethane, right? Staggered and eclipsed. This one is eclipsed. This one is staggered. Now stability. Torsional strain is more when hydrogens are with near to each other. So definitely your staggered form is more stable. Eclipse form is less stable. We have completed alkanes. We move to alkenes. What are alkenes? They possess double bonds. And hybridization and all, let's see. They have a pi bond. Hybridization is sp2. Okay, sp2. The sigma bond is an sp2 sigma. There is also IUPAC naming. Suffix is "in" instead of "in". Okay. Just a second, please. Moving on to structural isomerism, they show change in position of double bond. So they show variations in positions of these double bonds, apart from showing branches and all. Branches and all, though, they will show, just like alkanes were showing. But alkanes did not show any double bond. They don't have it. These have double bonds, so they will show variation in position of this double bond. Suppose the double bond is between C1 and C2. This is but1. Between C2 C3, this is but2. And both of these are position isomer 1 and 2. But between 1 and 3, you can see the chain length has changed. It is prop now. So 1 and 3 or 2 and 3 are chain isomers. There is one more thing called geometrical isomerism. Because they are planar structures, so the distance between XX here and the XX here, it is different. So these two are also a kind of isomers, and they are called geometrical isomers, right? Cis and trans. So in cis, both the same compounds are on the same side. In trans, they are on the opposite side. Okay. Now they have some properties, the cis and trans. First thing, for example, trans to butane is non-polar. Why? Because see, the dipole moments cancel each other. They are on opposite side. But cis to butene is polar. It has a dipole moment. Okay. Then in case of solids, it is observed that trans isomers has higher melting point than the cis form. Why? Because this is how the trans molecule looks like. So they can be packed together very efficiently. See, packing efficiency is much more. But in a cis molecule, it looks something like this. So yeah, it cannot be packed so well. So when packing is good, it is difficult to melt it because it is strong. This is weak. That is why trans isomer has higher melting point. Then they'll ask you to determine how they are prepared, how alkenes are prepared. From alkynes, how do you prepare alkenes? Heat them with hydrogen gas in presence of palladium and carbon. You will get a cis alkene if you heat them with palladium and carbon. If you heat them in liquid ammonia and sodium, you will get a trans alkene. Okay. The catalysts are, this is the trans one, and there you get a cis one. Again, for ethene, it is not defined. Even for propane, cis trans will not be defined. Okay. Then second is from alkyl halides. What is the principle you are doing? You are the alkyl halide, you are heating in alcoholic KOH. So what is happening? The alkyl halide is separating. It is taking an hydrogen with it and creating a double bond between the two carbons. Yeah, the reactivity is in the order of iodine, bromine, chlorine, and yeah, fluorine is very reactive, very less reactive. It won't show it. And tertiary, second, and primary carbon. This is the rate of formation of these kinds of carbon. Now, from vicinal dihalides, dehalogenation. So this one was dehydrohalogenation. One hydrogen and one halogen has been removed. Example of beta elimination. But what is beta elimination exactly? Exactly, if I tell you what beta elimination is, a hydrogen from the beta carbon will be removed if a halogen from the alpha carbon is being removed. That is beta removal. Now from vicinal dihalides, dehalogenation. So dihalides, that too vicinal, means nearby each other, next to each other. Look at this. Two halides are two halogen molecules are near to each other. Heating them in presence of zinc will just remove these two and create a double bond in between the two carbons. You get the alkene. Next example is from alcohols by acidic dehydration. This is also a beta elimination reaction and acidic dehydration of alcohols. Here, instead of a halogen, you have an OH. You remove an OH, you remove a beta hydrogen, create a double bond, you get your alkene. Difference is there is concentrated H2SO4 here instead of alcoholic KOH. Physical properties, again, like they are a bit polar. First three members are gases, next 14 are liquids, higher ones are solid. Boiling points, see, they're insoluble in water, soluble in non-polar solvents, we know, like dissolves like regular regular increase in boiling point with increase in size. Okay, this is their physical properties. Next important one is their chemical properties. So what you need to remember here is their rich source of loosely held pi electrons. So they show addition reaction. So what is happening in addition reaction? Just inverse of what you saw in preparation. A pi bond has been formed right between two carbon by removing something from these two carbons. So just break this pi bond. Okay, just break this pi bond, create a single bond, and open this pi bond and add some A and B product to this. You can add dihydrogen. A and B can be hydrogens. You can add halogens. A and B could be halogens. Example of addition of halogen is this. See, you are creating, again, you are adding chlorine and double bond. See, it is a single bond now, and chlorines are added. Okay, I add a hydrogen halide. Just like you removed a hydrogen halide, you can add a hydrogen halide. And reactivity is this. Their addition, they are showing addition reaction of HBr. Okay, with mechanism. Okay, first one is according to like how to add to unsymmetrical alkenes. What is the Markovnikov rule? So Marconico gave a rule: when addition of water is there, few drops of concentrated sulfuric acid, you can add OH and H to the molecule. Moving on, we have oxidation reactions. So alkenes will get oxidized to alkanes or diols on reacting with dilute KMnO4. See, diols. Acidic potassium permanganate will oxidize them to acid, ketones or acids. Okay. Then ozonolysis reactions. Not going to explain it. It'll take too much of time. Isomerism, polymerization. Simple. Just remove the double bond and polymerize it. Then you have alkynes. Just a second, please. Okay, so yeah, guys, we were discussing alkynes. So alkynes, just like alk now. Okay, I'll start. Okay, guys. So we were discussing about alkynes, and just like alkenes, they also contain multiple bonds. They are unsaturated, but this time they have at least one triple bond. At least one triple bond. So yeah, they might be having one triple bond, one double bond, and multiple single bonds, or they might be just be having one triple bond, or they might be having multiple triple bonds. But at least one triple bond is required to call them alkyne. Okay, this is the definition. We move on to the first stable member of alkane series is ethyne, because you the general formula is this: if you put n is equal to 1, it will it won't make any sense. Okay, so the first member is ethyne, n is equal to 2. Nomenclature and isomerism. Isomerism is shown is basically again position isomerism. No geometrical isomerism is shown now because see, this is the alkyne. It can only bind to one other atom. This carbon can only bind to only one other atom. So they cannot show geometrical isomerism. Why? Because the distance will always be the same. No matter how you arrange these, the distance will remain the same. So they basically show position isomer, variation of position of triple bond. These are some examples, okay, with their names. IUPAC name, see, IUPAC name, you just the see they are named as IN. Okay, the AN is replaced by IN. That is how you give them the IUPAC name generally. There are specific points you need to know, but in general, IN indicates a alkyne. Okay, structure of triple bond, it is sp hybridized orbitals of the carbon atoms are overlapped, forming the sigma bond. Then the bond angle is 180-degree. See, this is how it is a straight line molecule. There are two pi bonds. Okay, bond enthalpy they have given, it's not important. Bond length, definitely a single bond is shorter than sorry, a triple bond is shorter than a double bond and single bond. They have given the values, okay, for the triple bond, for the double bond, for the single bond is the longest. Triple bond is very strong, so it'll the attraction is really huge, so the bond length will decrease. Bond strength is very high, that is why the attraction is huge, bond length is less. Moving on to our point of interest, it is preparation from calcium carbide. Remember, CaC2. Okay, first, how do you obtain CaC2? How do you obtain calcium carbide? You heat calcium carbonate, obtain a compound called calcium oxide. Heat calcium oxide with carbon, you get calcium carbide. This calcium carbide, on putting on heat, like reacting with water, will give you ethyne. So yeah, you have your starting material here. The second reaction which you need to remember is from vicinal dihalides. See, vicinal dihalides, alcohol and KOH. Okay, alcoholic potash. Instead of dehalogenation, if they undergo dehydrohalogenation. See, if dehalogenation is happening, so yeah, just these will be removed and a bond will be introduced. So that will create an alkene. But dehydrohalogenation is occurring because alcoholic KOH is there. So you will also remove two hydrogen atoms. Now you have to introduce a triple bond in between. See, this is the first step. You remove one halogen and one hydrogen. Then you remove another halogen and hydrogen, and you create a alkyne. So only these two examples are there, nothing much you have to remember. Okay, alkynes are easy. Physical properties not significant. Okay, no need to remember any significant physical properties. Just like the previous one, first three gases, next state liquids, higher ones are solids. They are lighter than water, they are immiscible with water, they are soluble in organic solvents, their melting point, boiling point density increase with increase in molar mass. These 3 points, as discussed previously for others also, you need to remember for alkene. Now, chemical properties, acidic nature of alkyne. How? How is it shown? If you give sodium metal to an alkyne, you will get a monosodium ethynite. Give another sodium metal to this alkyne, it has one more acidic hydrogen. give you disodium ethylamide. Now, if you give sodium, nothing will happen. The next example is if you give, this is the acidic hydrogen, you give it NaNH2. So that will, NH2 and hydrogen will combine to create a ammonia, and you will get a sodium salt, sodium propionate. Now the acidic character is in the order of this. Okay, the more alkyl groups are there, the less acidic character. So alkyl groups, number of alkyl groups is inversely proportional to acidic strength of alkyne. Now addition reaction, again you can remove the triple bond and you can keep adding stuff. See, you can keep adding stuff. Z is some additive product. Z could be dihydrogen, Z could be halogen, Z could be hydrogen halide, Z could be water. Okay, let's try to just briefly see some these reactions. For adding hydrogen, again the same catalyst, just it will create a ethane. Sorry, your alkane. It will create an alkane. Addition of halogens, it will create a tetra bromo alkane, just like tetrabromopropane. Addition of hydrogen halide will create dibromo your alkane, and both are added on the same carbon, so they are geminal dihalide, in which two halogens are attached to the same carbon. They are not vicinal, okay, they are geminal. So this thing you can remember about the geminal thing. Next, addition of water. You add OH once, you add OH twice. So yeah, if you add OH to this again and create a single bond, so two OH are unstable, so a water molecule is eliminated. Remove this hydrogen, not talking about. A water molecule is eliminated and you get this. The same thing you get. Then propine, you add OH, again you get a ketone, or even aldehyde you can get. Then after addition reaction, polymerization reaction. Linear polymerization will give you just linear polymers. Okay. Cyclic polymerization will give you, in red hot iron tube at 873, it will give you benzene. Okay. Form benzene. This was all about your alkynes. Now, aromatic hydrocarbon, they are also known as arenes. Alkynes, alkanes, alkenes, alkynes, and arenes. Now, they contain a benzene ring, most of them. So they are classified as benzenoids, and non-benzenoids. If they don't have a benzene ring, they are non-benzenoid. These are some benzoids, benzenoids. Okay, these are benzenoids. Some non-benzenoids I will show you later. But first, let us see what a aromatic hydrocarbon is. See this. If this is a benzene, it has some positions. This is ortho. Ortho. This one is meta. This one is para. Again, this one is meta. This one is ortho. With respect to this carbon, then with respect to this carbon, the CH3 is attached to the ortho position. So yeah, orthozylene. This CH3 is added at the meta position with respect to the carbon 1. Again, this is added to the para position with respect to carbon 1. Now, structure of benzene, alternating double bond or KQ structure. We all know this is the structure of benzene. Nothing much to be discussed here. But it shows resonance. That is the reason of stability of benzene. These are the resonating structures, but this is the actual benzene molecule. So on the right side, you can see these two are the resonating structures, but this is the actual benzene molecule with its electron cloud represented. Okay. Now, what is aromatic? How do you define if it is aromatic or not? That is defined by aromaticity. There are three conditions. First condition is planarity. It should be planar. Complete delocalizations of the pi electron in the ring. Suppose this is some kind of ring, and only this much electrons are getting, like they are getting localized with each other. These electrons, these pi electrons are not involving. So this is not a aromatic compound. Next criteria is presence of 4n plus 2 pi electrons in the ring, where n is an integer. All three rules are known as Huckel's rule. Some examples of non-benzenoic compounds. See this anion, this cation. Okay. So yeah, now we'll see how do you prepare benzene. Preparation of benzene. First is cyclic polymerization of ethyne. We have seen. Next is decarboxylation of aromatic acids. Again, soda lime, heat it. This thing will come out. You get a benzene. Very similar. We have seen this in alkane preparation. Reduction of phenol is something new for us. So we'll just cover reduction of phenol. See, reduction of phenol. So phenol heated with zinc, you get a benzene. Nothing. Just remember. Physical properties, nothing. Okay. Nothing relevant you need to remember. Chemical properties, just remember they show ESR reaction, electrophilic substitution reaction. For example, nitration. What is electrophilic substitution is an electrophile which substitute the hydrogen which is attached to the benzene. This will be substituted for some other atom. This could be in nitration, this atom is NO2. In sulfonation, this atom is SO3H. In halogenation, it is a halogen. Okay. In Friedel-Crafts alkylation or acylation, either this is for alkylation reaction, it is an alkyl compound. For acylation, it is a acetyl group. Okay. Now, for nitration, what you need to remember is the reagent. For halogenation, the reagents. For sulfonation, the reagent. Whatever I am underlining. For Friedel-Crafts, the reagent. You need a alkyl halides. You need an alkyl halide with anhydrous AlCl3. Another alkyl halide with anhydrous AlCl3. Again, in Friedel-Crafts acylation, you need a acetyl group containing compound with anhydrous aluminium chloride. Now, excess of electrophilic reagent. For example, if you give 6Cl2 to a benzene and electrophilic substitution reaction occur, then you'll get hexachlorobenzene. Okay. There is one more compound called benzene hexachloride. That is different. That is addition. You need not to confuse both of them. Because this is occurring in dark, so no addition reaction. Dark means no addition reaction can occur because there is no possibility of breaking the double bond and adding something. First, you need to break now for adding. So that breaking will not be happening if you are not giving sufficient energy. And in dark room, there is no energy. Generation of electrophile. This is the mechanism. Again, you need to form the electrophile, then attack of carbocation. Carbocation will be formed and removal of proton. You can study it on your own. Lastly, we have addition reactions. Just like I was telling you, see, BHC or benzene hexachloride. If you give UV light and you give chlorine, excess chlorine, you'll get benzene hexachloride. Right. Combustion, again, nothing to remember, just burn it in presence of oxygen. And then there is ortho and para directing groups. Just remember which is ortho directing, which will direct the electrophile to ortho position. OH groups and all, which will direct it to meta. These are all ortho, okay, activating or ortho directing. Then deactivating examples of meta directing are this. And even halogens are ortho directing and para directing. Toxicity and all, forget it. We'll just move quickly to previous year questions. So yeah, in the following reaction, A is the product. This is a halogenation reaction using Markovnikov's rule. What will happen? See, just remove the double bond. This kind of carbocation will be formed. Okay. This will be formed. So this will lead to ring expansion. Ring expansion will occur and something like this will be formed. A pentane ring will be formed. And here you have CH3. Here you have CH3. This carbocation will come here. Okay, so this is going to be this carbocation. Once it has formed a ring, it will relocate. Here it is a secondary. It will come here and it will form this kind of carbocation. And here a bromine will be added. So your answer will be fourth. Next, two statements. Clemmensen reduction condition will give this, and Wolff-Kishner condition will give this. So Clemmensen, see, Clemmensen and Wolff-Kishner. Wolff-Kishner will remove complete hydrogen, complete oxygen here. Clemmensen will also remove complete oxygen. So first statement, COOH will not be seen. This is wrong. But second one is absolutely correct. So statement one is false, but two is true. This you will learn eventually. If you don't know what Clemmensen and this are, just go and study back. You will find it in your notes. Find out major products from the following reactions. Third question. So you can see this is peroxide. This has peroxide. This has NaBH4. So both will give, the same product, and that product, there will be no formation of carbocation here. Okay. This will be the pH3, right? This will be the first. Oh, yeah, this will be the first product. The second one will be this. So yeah, both of them are fourth. Next, the compound which will have the lowest rate toward nucleophilic aromatic substitution. Lowest rate towards nucleophilic aromatic substitution. So nucleophilic substitution, see, there are two deactivating groups here. There is one deactivating group here. There is one deactivating group here. One deactivating group here. So yeah, this is going to have the lowest rate because there are two deactivating groups. Next, the major product P for the sequence of reactions is major product P, zinc HgHCl. This is Clemmensen. Remove ILH4, phenyl, and H3O plus. So I think this is going to be the major product. The one giving maximum number of isometric alkenes on dehydrohalogenation reaction is. So for this, we have to rearrangement. You need to exclude maximum number of isometric alkenes. 1-bromo 2-methyl-butane. Draw the structure. Butane. 1-bromo 2-methyl-butane. 2-bromopropane. This is one. 2-bromopentane. 2-bromo 3,3-dimethylpentane. 3,3-dimethyl. So yeah, I think this one will be giving the most number of alkenes. No, dehydrohalogenation. This is not the answer. This one is the one from here, traded double bond here. One is the answer, I guess. So yeah, we are done with the chapter and relevant PYQs we have solved. Yeah, mostly the chapter is done. So yeah, all the best for your JEE mains. I wish you best of luck. Thank you guys.